Hey everyone, it's a little melancholy, or I guess bittersweet rather. This might be the last video unless something changes between now and next week. So let's make it sweet, okay? I'm gonna try to keep it short. This one's going to try to encompass chapter 12.1 and 12.2. Though it doesn't cover all the main concepts of it, I'm hoping that I can deliver the I guess the more important parts. And there's so many little details and even things like partial pressure, I am not sure if I'll be able to get through. But I think maybe you can do yourself a favor and at least maybe read through chapter 12.4 as an idea. I'm not too sure if you're even going to be willing at this point in time, but I will try to do justice to your learning. 12.1 and 12.2 is going to introduce the ideal gas law. So PV equals nRT. PV and T, you might feel familiar because if I divide both sides by T, doesn't it turn into that? PV over T, that's part of the combined gas laws, and that always equals N times R. I know that's a little bit weird, but for now, bear with me. I'm going to try to explain to the best of my abilities where that comes from and where you can use it and why we use it in general. Do you recall when we first learned about moles, we learned something about molar volume. That is volume that 1 mole of any gas takes up. Okay, specifically, any gas takes up at 0 degrees Celsius, or of course, 273 Kelvin. Not too many students ask this, but you should have thought about it instead of taking this for granted. The question you should have asked is, how the heck does that make sense? Think about it. If I have a hydrogen molecule versus a fluorine molecule, we learned about atomic radius. Hydrogen could be that small and that small. That could be my diatomic hydrogen. Fluorine, on the other hand, is large, or rather, you know what, just for the sake of difference, much larger compared to the hydrogen. So if hydrogen and fluorine as a gas clearly has a different amount of volume, how do both of them take up the same amount of space, and that is 22.4 liters? How does that make sense? Fact of the matter is, it really doesn't. But what we forget is that we're talking about molecules here. We're talking about microscopic things. In fact, something even smaller than microscopic. If I took a hydrogen molecule and a fluorine molecule, and let's say I put exactly 1 hydrogen molecule and exactly 1 fluorine molecule inside a jar, the amount of space that both of them would take up would be that and that. Let me try that again. The amount of space that hydrogen would take up would be that, and fluorine would be that. In other words, there is no difference from a practical perspective, okay? So I may be actually wrong in saying practical, because if we do it in a lab, sometimes there are differences, but for now, just to make things a little easier to understand, from a practical perspective, there is little difference in the volume taken up by either molecule. So what can we say about that? What does that lead us to? So ideally, we say there is no difference instead of little difference, okay? All gases or all gas molecules behave ideally, okay? Or, you know, it just, I use the word ideally sort of as an English sort of fleetingly, just very loosely. The word ideally, there is a lot more to what makes an ideal gas, and it is very important. Would you please read up on it in chapter 12.1, 12.2, okay, for more details on ideal gases, okay? But under the assumption that all gases behave ideally, okay, the amount of space that they take up, the amount of space that they have between each other molecules, the amount of traction that they have between each other, all of that is sort of constant and not going to be a factor when we look at its behavior. We can say that all gases will behave identically with each other because they are all ideal, okay? So let's have a little extra text. So, okay. So, if all gases or all gas molecules are sort of normalized into the same size and behavior, then the relationship of P, V, and T for 1 mole of a gas molecule should all be the same. Remember, we just said that every single molecule in gas form, assuming that they are ideal, all have the same kind of behavior, all kind of same amount of space, the same amount of distance between them, same amount of attraction, blah, blah, blah. And if that is the case, then the relations that they have in terms of pressure, volume, and temperature should all be the same as well. And so from there, that theory, we come to the idea that for every 1 mole, right, of, 1 mole of a gas molecule, the pressure, the volume, and the temperature for every single mole, every single type of gas is going to be the same. But of course, it's not literally 1 mole is equal to 1 to 1 to 1. You need to multiply by some kind of factor. And that factor is this R. This is what we call the universal gas constant. So I'm going to clear this. You can go back to this part of the video to see what questions I'm going to ask you to do. But clearing the screen in 3, 2, 1. Back to the equation, nRT. R is the universal gas constant. And that is 8.314 kilopascals. It in itself doesn't have a unit. We basically give it a unit so that all the other units will be, I guess, accounted for. It will be kilopascals, liter per mole Kelvin. Okay, another way we could write it is 8.314 kPa, L, mole to the -1, and Kelvin to the -1 to show that these are in the denominator side. Okay, and because this is a constant, it is not 4 sig figs, it is infinite sig figs. It does not count. But take a look at what the units present themselves as. kPa represents pressure, so P must be in kilopascals. L is because volume is in liters. Obviously, moles is in moles, and the temperature is going to be in kelvins. Okay? Again, this equation can only be used under the assumption that the gas molecules are ideal gases. Up until the end of high school, and when you get into university, you will always consider gases to be ideal. And then when you further your science knowledge, that starts to shift a little bit, saying, what if it wasn't ideal? And we delve into that. For now, gases are going to be ideal. Otherwise, it'll be impossible to do some of these questions. Now might be a good time to study some of the sample questions in chapter 12.2. I am going to try page 587, numbers 1 and 2 with you. I'm going to get you to do some homework after you read through the chapter as well. I think the concept, the main idea behind why we can consider all gases to be ideal for now is important. So please do so, even though reading might not be your favorite pastime. Here we go. Number 1. A neon gas in a sign has a volume of 42.5 liters at 25 degrees Celsius and 3.5 kPa. Calculate the mass of neon. Let's do it. The volume is 42.5 liters at 25 degrees Celsius, which I'm going to convert to Kelvins right away, 273, so 290. Okay? Pressure is 3.5 kPa. Calculate the mass. Whoa, right? So these are the kinds of questions you can answer now. This is basically stoichiometry, but for gases. So now we have stoichiometry for solids. We have stoichiometry for salt solutions, so in terms of concentration. And now that we have gases, we have connected pressure, volume, and temperature to moles successfully. And why can this question work out itself? Because P, V, and T, using the ideal gas law, you can calculate the value of N. And if you can calculate the value of N, you can definitely calculate the value of mass. Remember, it's neon gas. Okay, what is the mass of neon gas? And Ne is on its own. It's not that atomic. It's what is it? Noble gas. Here we go. PV equals nRT. Pressure 3.5. Volume 42.5. Number of moles, I do not know. The universal gas constant, that is 314, always given. And temperature is 298. That means the number of moles is 0.06003, but 2 sig figs is my shortest, so it's going to be 0.060. Okay. Okay. What is the molar mass of neon? That I actually have to look up. Give me a second while I do that. You might have your periodic table already ready. Good for you. Neon is 20.18 grams per mole. That means mass, being moles times molar mass, 0.060 times 20.18. That is equal to, sig figs again, 1.2 grams. I have 1.2 grams of gas. 1.2 grams of gas would fill 42.5 liters of space at room temperature if the pressure around us was 3.4, or if the pressure of the gas inside the volume, inside the canister or whatever is 3.5 kilopascals. Good. Clearing the screen to do number 2 in 3, 2, 1. Here we go. What amount of ethane gas is present in a sample that has a volume of 320 milliliters at 25.0 degrees Celsius, which is 298 kelvins again. Pressure is 420 kPa. Now, actually, I take it back. I don't think this is a sig fig. It's just 0.32. And same with this, I think that's just 2 sig figs. What amount? Amount would be the number of moles. I'm going to make it harder and ask you for what the mass would be, since ethane is 2 carbons and 6 hydrogens. All right, let's calculate. PV equals nRT. PV nRT. I have no idea how I'm going to get you to memorize this other than just either doing it or creating some kind of acronym. When I was in high school, I was an immature kid. So this is how I did it. If you erase the N, it sort of feels like the acronym, the letters spell out pervert. Okay, PVNRT, sorry, PVRT. Right in the middle of it is the N. Okay, if that works for you, amazing. If not, think of something else. PV equals nRT, okay? Pressure is 420. Volume is 0.32. Moles, I do not know. The universal gas constant is always the same. And temperature is 298. N is equal to 0.0542. Okay? Oh, sig figs. 54 moles. And okay, so what would the mass of this gas be? Well, the molar mass of C2H6 is 2 times 12.01 plus 6 times 1.01. 30.08 grams per mole. That means the mass would be, although the question doesn't ask you, I'm going to ask you to do it anyways, moles times molar mass. And that is 0.054, 30.08, which is approximately 1.6 grams. As you might imagine, PV equals nRT, there are 4 potential variables. Up until now, the first 2 examples asked you to find N, but I can always easily give you N or easily give you M so that you can calculate N. Then I might ask you, what temperature was this molecule found in? So you can imagine the question might reverse itself and ask you to give you conditions and whatnot. Again, study the sample questions. Remembering correctly, I asked you to read 12.2 because I think it's important. 12.1 also has some interesting things too, but 12.2 for now. Study the sample problems, and then get a chance to do page 589, numbers 1 to 10. Okay? I know, it's a lot, but I think you'll do you good. Practice it. You'll see more of it sometime in the future, I'm sure. And that's it. Good work for getting this far and keeping up with the material. I hope that if you do continue chemistry in the years to come, that you would give as much or even more effort as you have given me this year. Best of luck, and hopefully see you in the next term.